It's time to get started with the second installment of the Quantum Materials Colloquium. We are very happy that Mark Golden of the University of Amsterdam is here to talk to us about, well, you can read the title on the screen. Mark is an expert in angle results for the electron spectroscopy to measure, amongst other, band structures and do more fancy stuff, where he also, I believe, collaborated with the group of Henk here today, and I think also Enea is involved in this particular project. So this very much fits the topic of the colloquium series that we have in mind, and we are very grateful that you could come here on such short notice, and we very much look forward to your talk.
Okay, thanks very much indeed. Well, it's a great pleasure to be here, having had a small panic as my laptop screen slowly got darker and darker till about after lunchtime it stopped showing anything anymore. But I managed to prize the PowerPoint file out, and thanks very much, Mika, for the very good support, getting it on the MacBook where it even seems to be the right size. So I was asked if I could jump into a hole in your schedule this time last week, and I'm very happy to do so. It's always a great pleasure to be in Utrecht, so 2 Wednesdays in a row. Let's try and make it a habit of it, maybe, then I'll get to understand the bus system a bit better. So it's not about topology in the sense of mapping one-to-one onto the new QuMat gravitation grant, but it's a little step back and showing you some of the things that ARPES can do beyond just measuring energy versus K eigenvalues and getting into the self-energy of the interaction of the electrons. So maybe just for my own normalization, can you put your hand in the air if you're a theoretician? Okay. So I'll see how I pitch it on the way through. And as you can see, some of your colleagues are very important to this. So sorry, Henk, it's a bit of a taking calls to Newcastle for you. Let's see if you can keep your eyes open. But I'll tell you about this work in the following 45 minutes or so. So in Amsterdam, we have a cluster of principal investigators bound together in the name of QuMat without a U. So you added the U in between for your gravitation grant. So this is the quantum materials group. And we study quantum materials which have emergent properties. So these are properties which are not easy to predict from looking at the microscopic degrees of freedom of the system. And this talk will be about high temperature superconductivity. That's obviously a very much a poster child of emergent phenomena, and that's what this talk will be about. We also study complex oxides, metal insulator transitions, that kind of thing. 2D nanophotonics, that's in Jorik van Groep's group, and Anna Isaeva's group is very strong in looking at topological materials, magnetic topological materials, and we're doing that from the spectroscopy point of view as well. So this is the kind of stuff which we work on in the quantum materials sector in Amsterdam. So I'd like to show us at the beginning. I'll come back to it at the end, but I'm not quite sure how my timekeeping will go. So these are the 2 PhD students who are the main motor behind this project. Lots of other people are involved, also senior people like Henk and myself. We really enjoyed the ride, but these 2 young gentlemen were really the people doing the heavy lifting, and we were just learning from them and maybe giving a guiding nudge every now and then. So Steve Schmidt has his PhD now cum laude and is in the University of British Columbia in Canada as a postdoc in Andrea Damascelli's ARPES group. And Enea is just gearing up towards his defense. I'll be back in Utrecht again in 12th of December, if I remember the date correctly, because that's when he'll be doing his thesis defense. So there are a lot of people involved in the experimental beam times at synchrotrons, which gave rise to these data. So these people are listed here. These are the people who are providing the photons for these experiments in the Diamond Light Source in the United Kingdom. Crystals are being grown by my colleague, Yingkai Huang. So crystals are very important. So he's on the top line, but also we got some from University of Tokyo. And this was part of a national research program into strange metals, which I'll tell you about in a moment. And that involves strong interaction with theory, not just with Henk and Enea, but also with the colleagues from University of Leiden. So we had this, it was, I think, more or less one of the very last FOM programs, actually, and it got relabeled to an NWO program just as it got funded. And this is bringing together 4 different experimental techniques or groups. So angle result photoemission, optical spectroscopy, high field transport data, and scanning tunneling microscopy and spectroscopy. So approaching the electronic system from many different angles, and a pair of pairs of theoreticians, where one is more of a string kind of theoretician and the other more a condensed matter theoretician, with the idea to describe the physics of these strange metals, possibly with this intersection between string theory, quantum information, black hole physics, all things I don't understand anything about, and condensed matter physics in the middle. So this is a typical picture from a meeting of this consortium. So this is Dave scratching his head to work out how to understand the Zanian chalk hieroglyphs on the blackboard. And this is the postdoc Lewis Borden looking a bit concerned and realizing he'd prefer to go into data science as his next job rather than more of this. But in the end, we got to quite an enlightened state. This is, I think, the last Veldhoven bomb before the lockdown, where you could see quite a good team spirit developed in this journey of 4 to 5 years we all had together. So this is the solid state chemistry of the systems we're interested in. Basically, it's a kind of framework compounds where the main important thing, if you're concerned about reducing your Hilbert space, then this is the thing you need to take into account. It's a copper-oxygen plane. So it's a series of copper O4 squares, which are connected by their corners. So there are all kinds of different chemical names for these different kind of cuprates. You can have 1, 2, 3, or more copper-oxygen planes. The highest TC at ambient pressure is 135 Kelvin. If you put it under pressure, it goes to 150. So for us as physicists, it's half of room temperature, right? So we're halfway to room temperature superconductivity, at least if you calculate in Kelvin. So this kind of superconductivity is a huge theoretical challenge. The Nobel Prize for the discovery of the materials has been given, but still none for the theory behind this. So a chance for some of you here. It's very robust superconductivity in high magnetic fields. So no discovery of the Higgs boson without superconductivity, of course, but also not without high temperature superconductivity. So the cables between the room temperature bits of CERN and the low temperature superconducting magnets that send the protons around the corner, they're made of this material here, yttrium-bearing copper oxide. So electrical generators, superconductors are important nowadays. They're being put at the top of the windmills, so you can have smaller and lighter objects at the very top of the big power generating windmills. For cables, and of course, other kinds of superconductors are important as qubits. So superconductivity is very green. Netherlands is a country which doesn't see superconductivity as energy research. It's about the only country in the world which has this anomalous standpoint. In all other countries, it's seen as an important part of your energy infrastructure to do research into superconductivity and into transportation. So this is the future of flying, right? You fly at an altitude of 10 centimeters in a train going 500 or 600 kilometers per hour with high temperature superconducting frozen in flux magnets on the bottom of your train and an electromagnetic track which accelerates you and decelerates you. So this, if you've got the money to get to Japan, which you'll have to probably take a kerosene fueled plane to get there, you can then at least go between Tokyo and Nagoya. They've already printed the timetable. Japanese are very organized and very future looking, 2027, maybe with a small COVID delay. And this is, of course, in the end, how we'll get from Amsterdam to Vladivostok if we want to get there.
But the maglev in China is already operating.
Maglev
right?
in China is already operating, but that's the trans-rapid style of maglev. So that's one where you're basically using magnets and other magnets to repel each other. So that most of the train on the underside is electronics to measure where the train is on the track. This train stays stuck to the track anyway because of the flux pinning of the magnetic field lines inside the IBCA. So basically, you don't need to steer this train. You don't have to do any advanced electrical engineering to keep it on the track. So that maglev technology is 1970s.
Yes.
That's the trans-rapid in Germany. Okay, so it's a nice piece of solid state chemistry. As I said, there's this plaquette of copper. It's a 3D x squared minus y squared orbital. That's the highest orbital in the crystal field split structure. And there is one electron in there, and you have these 4 oxygen 2p orbitals pointing towards the lobes of this copper T x squared minus y squared. So for the material without any additional holes per copper, divalent copper 2+, so it means it's 3d9. So you have 9 electrons and 1 hole. For those kind of, which we call the parent compounds, they're antiparametric insulators. And they're antiparametric insulators because of the strong Coulomb repulsion between 2 charges in this copper 3d x squared minus y squared. So if you have d9, let's forget the 8 underneath, right? They're all filled, so they're not interesting for the physics of the compound. We have one band, which is half filled, and density functional theory will tell you it's a metal. You make it, you do experiments on it, you see it's an antiparametric insulator with a gap of about 3 electron volts. So this is immediately a signal to everyone in the field that these superconductors may be quite interesting because they're not born from regular Fermi liquid metals, but born from doped Mott insulators. So here's the phase diagram. As you add additional holes beyond this one intrinsic hole per copper, you get a superconducting dome appearing between about 0.05 and, depending on the compound, up to about 0.3. So the fact that superconductivity goes up is interesting. The fact that it actually goes down again is interesting. And this is the big challenge for condensed matter science to understand this phase-time. Okay, so there's strong Mott-Hubbard physics due to the Coulomb interactions between the copper 3D electrons in the copper 3D. So you have a lower Hubbard band down here, upper Hubbard band up there. This is about 10 eV, even after screening in the solid state. And the gap that you see in these cuprates, if you have energy going up to the right, is because I'm in between these two Hubbard bands and I'm the oxygen 2p states. So the gap is actually a charge transfer excitation from the oxygen 2p to the upper Hubbard band copper 3D. So this in the language of Jan Zahnen's PhD, U is greater than delta, so these are charge transfer insulators. Okay, so the extra doped holes, of course, don't go into this copper orbital because that would cost a zingy 10 eV to put another one in there. So they go into a symmetry adapted linear combination of these oxygen 2p. So the minimum model, really, if you want to start to think about this, is a 3-band Hubbard model. It starts to get quite theoretically difficult. Okay, so the undoped parent compound has very strong electron-electron interactions. There's a gap, and you get antiferromagnetism. Now, more people were theoreticians than not, so I don't need to show this for very long. You start with a metal, you get a Mott insulator, and oxygen 2p states in between. And it's understanding this charge transfer gap and what happens when you lightly dope this material, which is very important. So in sport, of course, you're not allowed to dope, but in chemistry and physics, we like to do this. So essentially, what these superconductors are not so different from the copper inside the cables in the wall here. You just rust it a bit and put a couple of elements in there and you get something emergent and totally not understood. Maybe even very important for our management of the energy problem. Okay, so in normal metals, of course, there are electrons inside materials. I work just across the road from NICEP, the National Particle Physics Institute, who are very keen on the standard model and the particles of the standard model. And of course, the electrons in a piece of copper are electrons like in the standard model, but they don't behave exactly like them. So we call them things called quasi-particles. So let's imagine a normal resistivity curve for a metal or superconductor versus temperature. So the resistivity, if it's a superconductor at some stage, will be 0. And then at the transition temperature, the resistivity will appear. Then you'll see some low temperature behavior where the resistivity will go as T squared because of the electron-electron interactions in the material. It's a phase-based argument to do with how electrons can scatter from below to above the Fermi surface of your metal. So even a piece of copper has this behavior. Then as the electron-photon kind of interactions overtake, you get something which can be quite linear. And at some stage where the mean free path length describing the scattering of these electrons get to be of the order of the interatomic spacing, you can't get more scattering than that, and the resistivity tails over. And this is called the Joffre-Regel limit. So this would be a superconducting resistivity curve of a regular metal, which goes superconducting at low temperature. So this would be this kind of behavior, right? You'd have a normal metal at some higher temperature, and this will become a superconductor as you cool it down. And of course, superconductors have things with magnetic fields I won't go into. So the Fermi liquid picture of Landau with quasi-particles describing the interaction of the electrons with each other, the interactions of the electrons with the lattice degrees of freedom, that can explain all of it in gruesome detail. It's extremely successful. So now let's go to these cuprate superconductors and look what a strange metal superconducting resistivity curve looks like. This is drawn with PowerPoint physics, but in fact, the right composition does look like this. So at low temperatures, you have a superconductor, resistivity is 0. At the transition temperature, the resistivity jumps up to a finite value. And even if this Tc is fairly low, so that this is a low temperature, immediately after the superconductivity fluctuations have gone away, the resistivity for some doping levels is perfectly linear. And it goes on being linear. It doesn't seem to care about Mr. Joffre or Mr. Regel. It just keeps going up and up and up, in fact, for some compounds until the material melts. So this is an iconic badge of strange metal behavior that has been a kind of red flag to our collective bull of theoreticians and experimentalists. We really want to understand where this comes from. So this linear resistivity is one of the emblematic mysteries of the cuprates, and this gives rise to a phase. On this phase diagram, if we think about the whole doped cuprates, so look on the right-hand side, you have antiferromagnetism, which you can understand in the Hubbard model because of the strong correlations. Then you have a superconductor, which we don't yet understand. And of course, the superconductor is the child of a parent, which is a metal. When we're cooling it down, there's a pairing instability, and the metal is less energetically favorable than superconductor. So if you want to understand the kid, you should get to know the parents. So we're interested to know what the physics of this strange metal is. Some people say on the right-hand side, things get more like the green curve again. I'll show you it's not actually quite that simple. So even on the very overdoped side of the phase diagram, where we're getting as far from the mod antiferromagnet as possible, still things are weird. Now, the fact that we've thought of nothing better to call it a strange metal tells you about the paucity of understanding we have. Right? We don't have a better name for it than we just find it strange. And we'd like to understand it. Okay, so what's going on in cuprate strange metals? Now, one of the things that can be going on in such a phase diagram here is the concept of quantum criticality. So a normal phase transition, I have my gin and tonic, there's an ice cube in, the ice melts, it changes this phase of matter from a solid to a liquid. That's driven by thermal fluctuations, can be described with Landau theory. But these kind of systems, for example, in a cartoon sketch, you could have temperature against some knob you have, let's say pressure, magnetic field, doping. Let's imagine you go from some ordered state to some disordered state. And if you do this at very low temperature, there are no thermal fluctuations and only quantum fluctuations available to drive this change in the state of matter. So we call this kind of point a quantum critical point. And luckily for experimentalists like me and the others here, you don't have to get to absolute zero to see the consequences of this. There's a kind of tornado funnel of quantum critical behavior which sticks up to higher temperatures. I think certainly tens of Kelvin, maybe even many tens of Kelvin. So we can do experiments to look at that. So one of the things that could be in this kind of phase diagram could be quantum critical points. Now, quantum critical behavior up to high T means we can see it. Quantum critical means scale invariant in space and time. Right? So those of you who are closer to the conformal field theory world will be in a happy space now. And if you measure things experimentally, then you should see scaling of these things you can measure with power laws describing both the frequency dependence, energy dependence, and the temperature dependence. Okay. So obviously you can go and buy this kind of quantum critical vegetables as well if you're interested in things which are scale invariant. So maybe there are quantum critical points down here. We're going from an antiferromagnet to something which is not ordered. We're going from whatever that is to a superconductor. We're going from a superconductor to something which isn't a superconductor. And many people think there is some line, if you take the pseudo gap line and this putative line describing a transition towards a more normal fermi-liquid-like metal, which I don't think is there actually, that there could be a quantum critical point hiding under more or less the maximum TC of these superconductors. And maybe it's this quantum critical stuff which is driving the unconventional superconductivity. So are they just regular quantum critical systems? Well, the answer to that is very clearly no. And here I show you some data from Nigel Hussey from the Radboud University of Bristol, who's one of the experimentalists in this program. And this is various different doping levels. The numbers here are not the TCs, but the doping level in percent of lanthanum and strontium copper oxide. So very simple single plane cuprate, excellent for transport experiments, very nice single crystals. Its surface sucks, so I can't measure it in photo emission, but otherwise it would be a great thing to measure. And you see doping levels like this 18%, which looks exactly like the PowerPoint cartoon of the resistivity curve I told you. You have zero resistivity at low temperature, a jump to a finite value, and then linear all the way. In this case, it was measured up to room temperature. But what Nigel noticed with his team is that all of these resistivity curves, maybe an exception to the very last one, none of them are T-squared like. They all have a mixture of T linear and higher powers of T. So there seems to be strangeness in all of these different compositions. So if you look at the power of the resistivity, increases as a function of temperature, of course, transport people have a very powerful experiment, and the only knob they have is temperature. Right? I'll be showing you later that we can change both frequency and temperature in ARPES experiment, but we're not as highly resolved as the transport people are. But if you look at the rho goes as T to some power n, this is 2 way up here, way beyond the superconductivity, and it's strictly 1 around the optimal superconducting temperature. So this is the superconducting dome sketched in. This is the superconducting fluctuation sketched in. So here it's really linear all the way up to very high temperature. But if you suppress the superconductivity with a high magnetic field, you see that there are linear components at low temperature all the way across. And it's at low temperature getting linear resistivity that's theoretically really difficult to explain, because there it's all the electron-electron interaction is driving the lifetime of the electrons. And so you should be getting this. These things have a Fermi surface. There should be this T-squared thing popping up if they're regular metals. So linear resistivity right down to the superconducting transition temperature means these things are really not a Fermi liquid. You have to put that aside And then the experimentalists are challenged. How do we even talk about our data, as all of the words and concepts we use are the ones belonging to this quasi-particle lifetime. So the theoreticians are then challenged to give us a new language in which to describe this, other than by just saying what it isn't. So it's linear right down to TC, and there's a linear component over a wide doping range. So what we discuss is this is what we call a quantum critical phase. So there's a whole area of doping down here, which is above the optimal doping. So the right-hand side of this superconducting dome, where all of these different doping levels look quantum critical, but they all have different power law scales, as you can see here. So this is really an area of phase space in chemical compounds, but that means in Hamiltonians, which are all looking quantum critical. So it's not an infinite number of single quantum critical points we can look at one after the other. We have to describe this quantum critical phase. So this is what the strange metal is. Very important to understand. So I put this rather facetiously. I hope you forgive me as an experimentalist. Can condensed matter theory deal with this strange metal phase? Now, the simple answer from Jan Zanen is this sheet, which I won't go through in any great detail. But basically, there's all this stuff, which means that the answer is no. So you have the fermion sign problem for those of you who have to tackle with the correlated electrons. So a copper-oxygen superconductor can be seen as the most entangled stuff we are aware of. So you have an Avogadro number of electrons. They're all strongly entangled in space and time with all of the others. You don't want to make your qubits out of this, right? There you want some weak coupling you can switch on and off and manipulate. So this is the ultimate test for theories that can describe quantum stuff, and would be the ultimate test in the end of a quantum computer, because that should be able to deal with these kind of things better. So it looks like in regular condensed matter theory, right? Also quantum critical theories, all of this stuff don't do the job to describe these kind of materials. Well, certainly if they do, it's a horrifically expensive computational price with some simplicity you have to add to about the chemistry, which you can wonder how many babies you're throwing out of the bathroom. So it's a system where the interactions are dominating. Okay. So this is what I paraphrased earlier. So it's maximally long-range entangled quantum matter. That's to sound a bit more like, yeah, you put all these words next to each other. So that's our situation. We look up from our valley as experimentalists, and on the hillside, just as the sun is coming up, we see the silhouettes of the cavalry coming to save us from our quandary, and that takes a very special form of cavalry in this case. And that's this connection between condensed matter theory and holography. So the anti-de Sitter formal field theory correspondence is, I think, something you're familiar with. There's a principle in physics that if you have a problem you can't solve in a certain number of spatial dimensions plus one time dimension, you can transfer that problem into a completely different physics computation in one dimension higher that you can do. And on the surface of that world lives in some mysterious way the answer to the question you couldn't answer directly. So these cuprates are essentially these copper-oxygen planes. So it's two spatial dimensions plus one time dimension, so they're 2 + 1 dimensional. The idea is that by doing calculations on Einstein's theory of gravitativity in 3 + 1 dimensional negatively curved spacetime, that's what the anti-de Sitter stuff means, with black holes and all the rest of this stuff that needs to be put in there to make it to work, you can actually say something about the condensed matter physics of these electrons. So that's the very attractive theoretical idea, and the question is, can we devise experiments that can test whether this works or not? And that was the joint goal we had with Henk and Anea to see if we could do that. Okay, so the ADS CFT theoreticians tell us they're honest enough to say this yields many, many different solutions, and it's not clear to them a priori which problem in the gravitational theory is exactly the right one to describe our electrons. Maybe there are 1,000 different ones. So to my ears, that's simply saying experimental control is very important. So can we use, now in my own personal language, can we use angle resolved photoemission experiments to see if ADS CFT works, or even stronger, to show it doesn't? These are the strongest experiments, right? For real data from one of these copper-oxygen superconductors. So holography is something which is done on a global scale. There have been superconductors coming out of this theory. There's been the Fermi liquid has been generated from this theory. You need to describe the stuff you understand with your new theory, right? You're not just allowed to describe the new stuff. You have to describe everything else as well. And this is a Dutch contribution to the field. And there are also calculations of the transport in the strange metal, which seem to come out from this theory quite well. So it's looking pretty good. this seems to be a relevant possible approach. So this is one of the Bibles of the field, holographic duality in condensed matter systems, Sun and Sun, Liu and Schalm. And I was very proud when they published this book, because this is a Fermi surface map recorded with my photo machine in Amsterdam that has been morphed into a sinkhole going into a singularity at the core of a black hole. It's been anti-de-Sitter in terms of its symmetry as well. That's not what the experimental one looks like. It's quite a simple bunch of these round things. But it's nice when the theoreticians are looking in their Bible, they first see an experimental picture on the cover. Okay, so how do we dare or try to connect to such extremely difficult theory? Now, the most important thing I would say as experimentalists is try to do the dumbest, simplest experiment you can do. And transport is, in principle, easy to do, but really hard to understand. So if you think of your maximally quantum entangled stuff as a plate of spaghetti, which hasn't had enough olive oil put on it and starting to cool down, in transport, you're pulling on one of these strands of spaghetti and the whole plate is sliding across the table, and you have to describe all of that. I do a much simpler experiment. I grab one of these pieces of spaghetti, I pull it really hard, and it comes off the plate, and I can just measure this simple object with a ruler without having to worry about all of the stuff on the table. So we want to do a simple experiment. We want to do an experiment that measures something all the theoreticians can generate data on, right, without having to think of a new way of doing it. So the obvious thing is to look at the spectral function, A of k and omega. That is baked into all of these kind of theoretical approaches, so people can immediately benchmark whether their data can explain our experiments. So all it means is the probability of removing an electron with an energy E or omega. I'll use them interchangeably, frequency, energy, without the proper natural constant, sorry for that, and a certain wave vector of k. And because I'm talking about these two-dimensional copper oxygen planes, we care about kx and ky, which is lucky because kz we can't measure very well with our experiment. So this would be the electron gas in spectral functions, right? Just a series of Dirac delta functions. Each time you change k, you change the energy. At some point, you cross the Fermi level. So these shaded ones are occupied and the white ones are unoccupied. Obviously, this stuff doesn't exist, right? Even gold isn't like this, but it's a good place to start with. And if you would add in a world of quasi-particles or quantum salad dressing, to use another Zahnian's phrase, you'll get something which will look like this. You still have objects with a well-defined energy versus K relationship. These are the quasi-particle poles of our spectral function, and a lot of interesting physics is buried in these tails at high energy, but they're experimentally quite difficult to access. So what you see now in the interacting electron system, and this is still only interacting at the level of Fermi liquid theory, right? So mildly interacting, is the width of these spectral objects will increase as they move further below the Fermi level. It's fair enough, right? I'm removing an electron from some sea of fermions, and the deeper I am below the Fermi level, the quicker electrons will drop into that hole, and therefore the shorter that state will be. So that's how we can try and measure the lifetime. So basically, we can try and identify these things, and people do that spectroscopically. Spectroscopists like peaks, and we're going to point at something which is peaky and say it's a quasi-particle. You know, we don't necessarily really know that, to be honest. But we can get out, of course, the energy versus K, so the dispersion relation that Ingmar related to. And that's useful to do in cases like this, where it's difficult to even calculate that accurately. But that's just telling you where these things are located, but not what their nature is. Their nature is embedded in their lifetime. So from the width of features, either in K space or in energy space, we can back out, if we measure them really carefully, how long-lived they are as a function of frequency range. So we measure a spectral function. It's cast in this kind of form here, where we will have an energy versus K coordinate, and we'll have what's called a proper self-energy, which has a real and imaginary part. And this is some old experimental data of colleagues of mine in Dresden before I came to the Netherlands. This experimental data is just shown in a kind of grayscale. You have some K Fermi, where this band crosses the Fermi energy. Obviously, the photovision stops then, because we can't photo emit electrons which are not there. And you can imagine some putative bare band. I've drawn one here. There's a straight line, but you could take a curved one if you like. And the real many-body spectral function is deviating from some simple bare band for two reasons. One of them is that you have a lifetime which is increasing as you go deeper below the Fermi level, and via Kramer's chronic conformity, that means the real part of the self-energy will be changing. And you can have things like this change of slope. Maybe you can see this dashed line that the slope of this thing is changing, and that's just recognizing that this material has things called phonons in it, and the electrons can scatter off them. So this is like the elk test for the Mercedes car, right? You drive towards the elk, you have to steer, you'll leave a big black stripe on the ground, which would be like a kink. So by looking at how this dispersion relation changes, we can back out what are the elementary interactions taking place in our system. So that's going beyond just looking at the band structure, right? And that's not in the local density approximation of DFT at all. Okay, so by looking at the width of this object parallel to the k-axis, if we know the velocity, if we want to assume a velocity for this bare band, we can calculate the self-energy in energy units. Okay, so how do you do ARPES? It's really easy. You need a friend who's very skilled at making you a single crystal because we care about Kx or Ky or the diagonal. So we need a macroscopic bit of stuff where all the atoms are nicely arranged. We call it the single crystal. You need a photon source, unfortunately, with a little bit more energy per photon than this green laser. So the price point for that is not $50, but 50,000 or more. So you need to get the electron out of the solid. You need to overcome the work function. So you're thinking 6 eV up to hundreds of eV. And out flies a physical standard model electron, a physical electron. This is no longer some weird quasi-particle, right? It was some strongly interacting difficult stuff in the crystal, but I've removed it in attosecond speed. Auto emission is very fast probe, so the system has no time to say ouch and reconstruct itself. And by looking at the energy versus K relationship of this and its width, we can back out what the life was for this little red electron in the crystal. Einstein's formula for which he won the Nobel Prize, we are looking at the binding energy of this electron in the solid. That would be 0 at the Fermi energy, and getting larger and more positive as we go below the Fermi level. We know how much energy we brought in our photon, and we measure with a piece of apparatus the kinetic energy of the electron flying in a harmless piece of vacuum outside the cell. So we do that with a tool like this, just to put the theoreticians sometimes out of their comfort zone in the talk as well. This would be the sample. You'd imagine, of course, photoelectrons are flying out of this sample at all different angles. Unfortunately, we don't have a gizmo that can measure all of them straight away. So what we have is a set of electrostatic lenses which can sort these electrons with regards to their angles. So let's say the sample is the floor of this seminar room. My head direction is normal emission, right? So Kx and Ky are 0. There's only Kz. This one would have some Kx. That beam would have some Ky. That beam would have some Kx and some Ky. So we angle sort the electrons first, and then we need to energy sort them. So if you want to energy sort something, you do it just like the Formula 1 races. You have a nice tight curve, and the car's driving in too fast. They fly out of the curve. The car's going too slow. If they steer too much, we'll go on the inside into the Ringflag. So that's what we do here. So all of the electrons with a given emission angle, like the red beam, 15 degrees to the left, for example, they get spread out in the opposite direction in energy, and you end up with a distribution on your detector. So this is what such a simple experiment looks like if you want to set it up in your garage at home. This is a rather large laser, which offers us 5.9 to 6.3 electron volt photons. So this is quite an expensive laser pointer. This you can just see. This object, which looks like a hemisphere, is viewed here from above. So this is the first floor of our science park building. All of the students of the whole science faculty go past, and apparently each different study direction has their own idea what this machine is. We haven't labeled it on purpose. So the biologists think it's a time machine, apparently. So they see students coming in looking happy and young and without any gray hairs and leaving 4 years later looking a bit more concerned. No, that's not true. They treat them very well. So here's Dave sitting in the lab, and Samuel, one of the postdocs. So all of this hardware you need to get financed, and I'm grateful to both NWO and the University of Amsterdam for doing this. So on this measurement computer, which is down here, what do you see? This is just a smartphone image of the measurement computer. You see a piece of angle. This is plus or minus 15 degrees. You want me to see at the back. So that's a certain line in K-space. Right? If it was 0 would be normal emission, that would be Kx is nothing. Going to Kx is something plus, Kx is something minus. And we have a certain amount of energy because we turn these electrons around the corner to stretch them out in energy space. And what you see is this flying comet. This is simply the band. And because we're measuring, we can only measure the many-body version of this. We see that its width is changing as a function of its energy away from the Fermi energy, and that's related to its reduction in lifetime. You can see the kink here is changing its slope. If you very simply say it'd be linear with this slope, linear with that slope, you can get out the lambda for the electron formula. So it's this thing that we're going to be spending, I'm going to be torturing you with for the next 10 minutes. And this is the cut through the data in the angular direction, which means the K-space direction. It's called momentum distribution curve. And from the shape of this and its width, I'll be telling you about its lifetime. Yes, Vic.
Could you just say how long it takes to do a measurement like this? Are we talking seconds, minutes?
So this is using a laser, which has a lot of oomph, actually emits too many photons. We have to throw many of them away. So something like this would be a matter of a few minutes. The ones I'll be showing you that we actually use for the analysis with Henken and Ayer, because we wanted crazily good signals to noise, we were taking at the synchrotron, which is also very intense light, so it's about 2 hours per go. Okay, so this is where we went to do these experiments. Oxford's just down that way. It's actually much closer to a rather grubby town called Didcot, but they prefer to say it's close to Oxford. There's a bunch of electrons being sent in a ring. In fact, it's not a ring. It's a bit more like a British 50p piece with straight sections and curved sections. And along these straight sections, the electrons are made to wiggle through magnets, and they emit lots of photons. And people like us can go and compete to win beam time there. So it's a slightly embarrassing moment to arrive at one of these, because they'll say, oh, when can we come and measure at the Dutch one of these? And the Netherlands is just about the only civilized country in Europe which doesn't have a synchrotron. So I hope they come and use the Nijmegen Highfield facility. At least we've paid them back. So this is Diamond Light Source in the UK. So this is basically funded by pharmaceutical companies. You do drug discovery here by doing protein crystallography. So you need the physicists to build it. You need the pharmaceutical people to get the government to pay for it. Maybe because we don't have a pharmaceutical industry in the Netherlands, that's why it's tricky. And then the physicists come in as parasite users like me and do fundamental physics using the same tool. Okay, so maybe I skip this one to say, what does it look like? So this is a planned view of an energy K landscape. So imagine you're already thinking about your skiing holiday. You have 4 very symmetrical mountains at the corners of your Brouwer zone. The valley is at its deepest at the center of the Brouwer zone. That's the gamma point. So there's a very high energy where my laser pointer is here, the very lowest energy there. And the Fermi surface is then something like the tree level of your landscape, right? So at some level, the tree stopped, like the electrons stopped for me. And that's what this Fermi surface looks like. So it's not quite circular, it's not quite square, it's somewhere in between. And the fact that the area inside this object is larger than the area outside this object is telling us it's smaller, than the outside is telling us it's holed up. So if you did your 2D Hubbard model with exactly half filling, your Fermi surface would be a diamond. Exactly the same number of electrons. So we measure very carefully, or these are the numbers for the experimentalists. We pick samples which have quite a low TC. So the highest TC is 30 Kelvin because we're interested in the normal state. And if we take a high TC sample with a TC of 100 Kelvin, we could first start to measure at 110. So it's too much thermal energy. So on purpose, we're looking at low TC versions of the cuprates, so we can study the normal state even at low temperatures. Okay. So this is an example of a data set. It's one of the best ones we ever measured. So this is about 3 hours of just really willing yourself not to press OK on the computer and stop it, because you don't notice as this is scanning after the first 15 minutes, you don't see it getting better anymore. So you have to keep downloading the data, zooming in and looking at these little contours in the background, which are really, really perfect. So this is, okay, this experiment has been done on this material since 2000. We were doing it in 2020, so you better do it better than anyone else has done it. And otherwise, what's the point? So here we see we're going from one Brouwer zone diagonal to the other. The gamma point is in the middle. This band is somewhere down here. And then we're crossing the Fermi energy up here. So from this central, where my laser spot is from here to here, is KF. Okay. And this is KF in the other direction. So we have 2 symmetric bands. We're very careful to align our sample as perfectly as possible to get these things as equal as possible. That gives us one single pixel of information for our story. Okay, so this was our self-energy, our spectral function. With this kind of form, we'd like to know what this self-energy is. And usually what photometry people do is they say, okay, if we zoom in close to the Fermi level, then we can assume the band, the underlying bare band, which is a crazy thing to talk about because it doesn't exist. Right? There is no bare band. But if you think, okay, I have some velocity in my problem, let's call it a linear dispersing object for the sake of argument. And let's also assume that the self-energy is dominated completely by its frequency dependence. So there's no K dependence on the self-energy. If you do those things, then what comes out for your spectral function is this thing. And if you're an experimentalist and used to fitting data, you will recognize this formula as a Lorentzian. So it's a Lorentzian where the imaginary part of the self-energy is half. If we would cut through this thing and get a peak, it's the half width of that peak. which we need to multiply by some velocity to get it in EV terms, but we can just quote it in reciprocal angstroms terms, and then we don't care what self-energy someone wants to prefer, velocity they want to prefer. Okay, so what we're doing, this is an example for the highest TC sample we measured. This is just 1/2 of this distribution. We measured both sides. And then if you cut this at the Fermi energy, you get this very narrow object. Of course, in principle, right, if this was a Fermi liquid and our sample was perfect, this would be a delta function. Of course, I can't measure that, so it's a delta function broadened by my instrumental resolution and also by things like impurity scattering in the crystal. So this is essentially as close to 0 width as we can get it for these kind of materials. So this is a fit with a Lorentzian curve, which is what you expect from this kind of spectral function, convoluted with the Gaussian, which is our resolution that gives you something called a void. So this is one single energy. Now we can move this dashed line down and slice and slice and slice our data and refit it each time, right? So we have many, many frequencies. The steps in frequency are 3 millivolts. So we've got hundreds of spectra going down in energy. And this is one particular doping level, and this was measured at 8 Kelvin. With other ones, we're going to measure at 8 Kelvin, 25 Kelvin, 60, 80, upwards, something like 14 experiments, a function of temperature. Temperature is a horrifically expensive parameter to change at the synchrotron. You have to very slowly, gently warm up the sample. There's lots of hydrogen has condensed onto your cryostat, and if you do that quickly, it will make what we call the hydrogen fart, which will kill your sample surface. So you have to be very patient. Then you have to repeat all these measurements again. And then we want to do that over all of the samples we have. So 1, 2, 3, 4, 5, 6 different samples, and this is adding up to something like 3 weeks of permanent measurement at the synchrotron. We're very grateful to the people who award the beam time that they actually gave us a third go, because usually it's 2 times. Then the tab closes until you write the paper. So if you do this at these different frequencies, you will get such a curve. So this is now the full width half maximum of this distribution. So half of this would be the thing related to the self-energy. And it's as a function of frequency, because we can start at the Fermi level and move up to higher binding energy. And then we do it at different temperatures, and they're color-coded. I don't show all of them because it would get too busy. So this is just the experimental data. So now we want to do some fit to it to extract some theory parameters. So there's a suggestion in the literature back in 2019 that you can describe the electronic self-energy as one of what's called a power law liquid. It's phenomenological. It's not based on a microscopic theory, but says we have some power law describing the frequency and temperature dependence of the imaginary part of the self-energy. Frequency dependence goes as frequency dependence squared plus some constant times the temperature dependence squared, and all of that to some power alpha. So if you want to have a Fermi liquid, alpha will be 1, and you have omega squared T squared. If you have alpha of 1/2, you will have omega T. Okay. Now there is a phonon in here. You can see this kink in the self-energy, so we've added in electron-phonon coupling term just so we can properly do a fit, which determines these parameters here. Okay, so these dashed lines are a fit with this power law liquid plus a phonon. It works really, really well. So we do that for 32 Kelvin. So now I'm moving through the doping phase diagram. We're slowly reducing our TC. We even go outside the superconducting phase. So where people are saying, oh, that should be a Fermi liquid, right? So that should go to omega squared T squared. We redo this analysis every single time. This is 2 years of a PhD student's life to get 5 doping levels, 39 different temperatures, and get it all measured at this quality. And if we fit all of these data, that's the ones I've shown already, we can, for example, plot this alpha as a function of doping. So here's the superconducting phase diagram. We're looking at this part here, the overdoped part. Colleagues in the US who developed this power law liquid formula, they were looking at the underdoped part, and it really, really suspiciously just lies exactly on top of each other. So there seems to be a linear growth in this power law. So it's omega squared plus T squared to the power alpha. And alpha optimal doping is exactly 0.5. So I show that a bit bigger on this side. So at optimal doping, it really is linear. So the transport is showing us a linear behavior versus temperature, and the photoemission is showing us a linear behavior versus temperature and frequency. And if we wanted to get to 1 for alpha, which would be the Fermi liquid, we'd have to go up to a doping level which chemically cannot even be made with these crystals. Right? So our sample, which is outside the superconducting dome, that still has an alpha of about 0.8. So that would mean it's omega to the 1.6. T to the 1.6. Still not a Fermi liquid, even though it's non-superconducting. Okay, so the picture so far, we see these power laws. It looks like other people's data from higher TC samples. It looks like a quantum critical phase. And one of the things we discussed in one of the meetings of this NWO program was that we saw some hints that the line shape of these spectra was not completely symmetrical Lorentzian. And this light bulb moment went on in Henk's head, and he saw that, and that leads to the last part of the talk, which is actually the most interesting one, but I needed to introduce this so you know what we're launching off from into the ADS CFT. So what they've noticed is if you take, it doesn't matter which data because they all do it, if you take the momentum distribution curve at the Fermi level, so at k equal to kf, this thing is a Lorentzian, right? We have extremely good signal to noise. The signal to noise on these data is about 300. So that means the signal at the peak is 300 times the up and down of the noise away from the peak. So this means we feel comfortable to discuss what the peak is doing away from its maximum. And if you then go to 200 millivolts below the Fermi level, so this is some k vector, I don't know what it's going to be, 0.1 reciprocal angstroms below kf, you start to say, it's okay, but the fit is always giving us a bit too much intensity in between the two peaks and a little bit too little on the outside. We go to 300 millivolts, it's getting even more. So you can still get these power law liquid power law exponents from this kind of fit, but we're not happy. We're missing something in the data. So the residuals are getting larger and larger. It actually looks as if it's not what's happening. It's not the microscopic physics. You've taken these two peaks and essentially they're tilted a little bit outwards. So wrong way, in. So in between there, lower intensity than what you expect, outside they're not. So this means, that's why I have my earthquake logo. These are not Lorentzians. So it's the first time anyone's had the stupidity or guts, depending on how you want to look at it, to say, I really have done such careful measurements that I'm willing to say this involves some interesting physics and not just experimental artifacts. So we're convinced that this asymmetry, so the fact that this is not Lorentzian, is a part of the spectral function, not a part of it. It's a feature, not a bug. Now, this is when Henk said, but this is obvious, dear colleague. Your self-energy has to be k-dependent in these ADS CFT models, for example. This exponent, in fact, has to be k-dependent. This alpha has to have a k-dependence. Because we were racking our brains, how do we could publish a really quite dull experimental paper saying, look, it's asymmetrical, we don't know what that means. Or we could make something saying, okay, we're going to say the symmetrical part plus a k-dependent part, some Taylor expansion, but we don't know what it means. So we're really happy when Henk and Inea said, I think we have something which gives this whole thing meaning. So that's when Henk and Inea arrive. They're saying power laws like those of this power law liquid, where each different doping level has its own power law, right? This one was 1 for the optimal doping, going up to 1.6 for the overdoped samples. That's a natural thing in this ADS CFT world. So that fits nice. But there's an absolute condition. This is not some nice to have thing that Henk just likes because it fits his worldview. He can't not do this in the theory, that the alphas, these power law exponents, have to be dependent on k. So when k is equal to kf, there's no k dependence there. And as k minus kf starts to grow, these things, these alphas, have this k dependence, and that means the line shapes have to be asymmetrical. So Inea and Henk chose this Gupse and Rocha model, a semi-holographic model, which can be solved both analytically but also numerically. And you have this kind of formula coming out from that model, where you'd have your h bar omega squared plus b kbt squared to some power alpha, but alpha is a function of k in the sense that it's 1 minus kf over kf. So when k is equal to kf, alpha is just alpha, and as you go away from kf, this alpha is in fact changing. So we can rhyme everything again, but with a very important message coming out. So they generalize this to different temperatures. This is the spectral function rolling out of Inea's calculations and Henk's calculations. So that means they're in possession of the detailed physical self-energy from this ADS CFT semi-holographic model, and we're testing it with experiment. And if it survives that test, that means this is a very rich source of information. This can be used to calculate optics, can be used to calculate transport, any experiment you learn. So you see in their data also very clearly that the momentum distribution curves are asymmetric, just the same way as the experimental ones. So we needed a fitting formula we could use to really fit the experimental data, and that's the one that looks like this, with this alpha in it. And we have a 50 parameter V, which should be 1 in their semi-holographic model, because it was the alpha outside 1 plus thing. And we'll see about that in a moment. So we repeat the data analysis, 5 dopings, 39 temperatures. We fix the other bits of this parallel liquid to be the same as they were at the Fermi level. And then we don't actually have any more parameters to fit experimentally than we did in the old model. That was the clever thing coming from the collaboration with Henk and Ney. So we have excellent fits, and as you can see, the asymmetry is just rolling out perfectly. And the only thing we're able to tweak in this fitting is what the value of this V is. In this case, we took it to be equal to 1, which is what is demanded by the theory. So let's zoom right in, right? This you can only do if your signal to noise is like it is here. The peak is 2 floors up, or at least 1 floor up. And this we're able to discuss these kind of flanks because we have such good signal to noise. The data are the little crosses, and the symmetric Lorentzian fit is the red one, and the asymmetric non-Lorentzian fit coming from the ADS-CFT theory is the purple. So we have a K dependence experimentally shown to be in the power law in these systems, and the K dependence is linear in K away from Kn. Okay, so this is the pièce de résistance from these 2 young guys. So I just put it on once more, getting data of this quality and getting to a theory which can explain even the minutest details of this data, but without putting in a bunch of banana coefficients that Enea just can term depending on the weather in Italy. No, this is really based on a pretty locked down theory coming from semi-holography. So we have the self-energy, the electronic one, optimal doping, that's this guy. We have the electron-phonon interaction that we've modeled as this green one. You add them together, you get the experimental. In fact, this is the experimental self-energy minus the electronic one, gives you this green curve, and it looks exactly like a step at the phonon frequency. Okay, so there is this full theoretical self-energy, and now it's people's job to go away and use it, because it's been experimentally validated. So 2 last tests. One of them is we have in this parallel liquid some coefficient in front of the temperature dependence. This is the balance between temperature and frequency, right? You have frequency squared plus something times temperature squared, all to this power alpha, which is K dependent. So this beta from the parallel liquid fits in experiment is coming out somewhere around about pi and going up slightly. And Henk and Ney are very honest people. They just tell us what comes out of their theory. Now the trend is perfect. It's a little bit on the low side. But there's maybe some space to tweak the gravitational side of the ADS-CFT model to make this fit in the future. But it's the right ballpark for sure. Second one is a more stringent case. We then allowed the fit to work with this K dependence of the power law left free. It's a little bit scary because we have added 1 extra parameter to our fits, right? And we had to be careful how to do it, that it didn't go uncontrolled. So if it would be 0, you're back to your Lorentzian world. If Henk and Ney's model is strictly correct, it will be 1. And what you see is it's closer to 1 than to anything else. These are different temperature TC samples, all measured at low temperature here at 8 Kelvin. And you see as a function of frequency, they all share for the first 150 millivolts. It's closer to 1 than anything else. So this is, I think, a very strong test of the theoretical picture. Okay, so take-home messages. Strange metal cuprates are quantum critical phase. They show doping-dependent power law exponents, which we could see in the transport as a function of temperature, but in photoemission, we can see in also the frequency dependence of these systems. Our newest data are the first ARPES data to show in a really controlled way that the self-energy is not only a function of omega, but also of K. So for the theoreticians, that will sound obvious. But the experimental ARPES community has been, in 20 years, has been obsessing about the fact that it's only the frequency dependence that matters, because otherwise I can't use my Lorentzian and I don't know what to use. So the semi-holographic model of Enea and Henk's shows that ADS-CFT does do a great job to compute experimental data. So this says you are leaving the phenomenological sector. Street sign stolen from Berlin. So it shows us we have doping-dependent power law exponents, and these power law exponents are K-dependent. So I think that's the good point to stop. So thank you very much indeed for your attention. Sorry for running over a little.
Yeah. Questions?
Yeah, I don't speak Russian, the sector phenomenologique. So I presume this is phenomenological, this one, right?
Yes.
Okay, so someone should tell me what that is in Russian. That would be cool.
Daniel?
Yeah, so you showed that this semi-holographic model works, but that still leaves me a little bit not satisfied because can you explain this in words to normal people what this means in terms of the electron interactions in this model?
So I think this, I have to be careful. This is the first time I have to answer such a question with Henk in the audience, so I have to really think of my answer in an adult way. It's not trivial to have a physical microscopic picture of what's happening with those interacting electrons in our crystal. Right? It is something which is obviously very strongly coupled. It's something which is very obviously scale invariant and quantum critical. Otherwise, these theory approaches wouldn't work. So we know those ingredients are in the cake. So how to say this is exactly what's happening in the microscopic world, that's actually the next step, right? So we now know that there is a theoretical approach which can describe these kind of experimental data. And the challenge is for the rest of condensed matter theory who don't do holography. Now, on the test data is there. We're gonna share them with everybody. Come with your theory and get this too, including whichever series of microscopic interactions you need.
So let's assume a piece of the strange metal, I
Yeah.
move one electron little bit, I don't eject it.
Yeah.
What happens to the wave function? That is what you, the materials wave function, that is what you want to ask for, more or less. Is it?
Yeah, so we remove it to measure it. I mean, we're measuring, in fact, the behavior of that hole that we've left behind in the crystal. So we are measuring a property of the sample, not just of the electron in the vacuum. And I think the big challenge here is nature has guarded this secret very carefully, right? So high TC superconductivity is a very special thing. Regular superconductivity, we understand everything about, and this doesn't, on the face of it, look at the very first day to be all that different, except the parentage of the superconductor is different, and nature hides it, right? Makes this material chemically complex. So you need multiple orbitals. So if you're going to do an expensive quantum calculation, your Hilbert space gets huge, and you can't compute these things. So I think we're getting close. The experiments, ARPES has grown up because of this field. STM taken a huge boost because of this field, the technology of these experimental techniques, because this is a ginormous mosquito bite that we have to professionally scratch, right? There's a group of people, we can't not solve this problem. And there's a huge number of Nobel Prize winners who won their prize for something else, who came into the ITC Commons saying, okay, just give me a year and I'll have it. And most of them are, okay, most of them have died in the meantime, but they didn't succeed. This is a really difficult problem for humankind. Let's imagine an optimistic scenario, right? That we get to understand this stuff properly. It doesn't look like the cuprates are going to go to 400K, which is what you'd want. But maybe the right theory can give a pointer. I don't think that holography is a theory to point to the periodic table and say which mixture you need.
More questions? Peek behind the screen. Rembert?
Yes, I know one relation between your spectral function and let's say the rho, the resistivity data, T to the power.
Good question. No, not necessarily. So of course, transport is a Fermi surface integrated quantity, right? If you're teaching condensed matter physics, you have some Fermi sphere which gets shoved to the left because of an electric field, and depopulating states are populating new ones, and that's how we teach it to beginning second year students. So here we have a single cut through calculus. So the next thing, now that we've got this paper on the archive and are fighting with the referees of nature physics, is to go back to the single. So now we want to move away from that special zone diagonal. That is the area where superconductivity is zero, this nodal line, so we can measure at very low temperature without having a superconducting gap. And we're doing other experiments which look at the behavior of this. It will take me too long to get there. Look at the behavior of of this thing as we move away from this this diagonal of the Fermi surface. But it gets difficult to do exactly the same analysis, because if you remember the ski landscape analogy, the gamma point is the very bottom of your valley landscape. You have these four big hills in the corners, which are way up there. And in between these mountains, there's a high valley in between. So that means the band bottom gets really close. So if you would start to cut away from the zone diagonal, then you'll have a little comet here and a little comet there, and the bottom of the band will be just under. So you don't have much space experimentally in terms of different frequencies to try and do this analysis. So we'll start by moving just draw the semi-surface. Yes, thank you very much. Okay, this is the gamma point. This is pi 0, 0, pi, pi, pi. So now we will measure in this direction. And we'll just start, if we get the beam time in the first half of next year, we'll just try this one. And this one. And we're doing other experiments where we're cutting it in that. We'll see how far we can push it. I think this one will be not possible to do this kind of analysis, because if you look, maybe I should draw it in a perspective drawing. Let's imagine this is one of those Fermi surface segments, that's the other one, and now we're looking at energy. This is EF, and this band is just a little electron pocket below the Fermi level. Whereas if you're looking at this diagonal here, that's something going all the way down there. We've discovered all kinds of, we discovered that we don't have a good Fermi liquid reference material which we can measure and show is omega squared T squared either. But you're quite right. Transport is Fermi surface integral, so we have some work to do. It seems to line up perfectly for this. There are ideas about why this nodal direction is very important to do with small angle scattering, dominating in transport.
But just one comment, what I find surprising is even though there are no quasi-particles, as you've said many times, then you still say, let's say the transport you still think of as some integral over the Fermi. That
Yes,
doesn't have to be.
I agree. So this is something where I mean, the ADS CFT world, which is working very well for this optimally doped sample, is saying not only there are no quasi-particles, there are no particles.
Right.
It's non-particle physics, unparticle physics. Okay, I can show there are standard model things in there because I can remove one of them and it goes around the corner like an electron with charge E experimentally. And so we get into a language problem about, okay, we're still going to have to talk to each other about it. And we'll use things like Fermi surface integral. No, there's no Fermi surface. It's ultimately doped material. If you don't have a particle, you don't have your quasi-particle weight is 0, you don't have a Fermi surface. So then we start to have discussions about, we measure with photovision from this point here, and we get some spectrum which looks like that. We measure from this point here, and we get some spectrum that looks like that. Depending on the doping level, we have other ones where the spectrum just looks like this from this point. So there it really looks like it's completely incoherent. And as a spectroscopist, we find really hard. So how peaky does something have to be before we say it's a quasi-particle? I mean, the theory answer is clear. Its lifetime in energy units should be less than its energy. That's the Landau criterion, but that gives all real experiments a tiny bit of space around here where it may just work.
Yeah, but what is also well, my question is, but what is not so clear to me is that if you measure, let's say, the lifetime as a function of K and omega, that then there's actually a computation that will take you to resistivity.
No, it won't. No, it won't. No, it won't. So you have to do. It's a different response function, right? This is a single particle response function, and transport is a two-body thing.
Right.
So that was the whole idea of the makeup of this NBO program. You have Milan Allen and me doing single particle stuff, right? STM can push electrons in or pull them out. I can only pull them out. And you have DC and AC conductivity. DC conductivity, Nigel in Nijmegen, and AC conductivity, Eric in Amsterdam with optics. Those are these collective degrees of freedom. So the big discussion going between the theoreticians and experimentalists like Nigel is this behavior he's seeing as you're going across the different doping levels, how this thing works, and also weird stuff happening with the Hall number in these materials. So which part of this Fermi surface is really where the non-particles are sitting, and which are things where we say, no, there's still something which, I mean, that's not possible in holography, right? It's kind of mixed. You have some bit of K-space. I mean, there's no K-space in these holographic theories yet. So I agree there's some friction, certainly in the language we use. Of course, the more formally theoretical you are, the more that troubles you. So I fall asleep okay in the evening.
Excellent.
One final question, if there is one.
There was one at the back.
Yes.
Yeah, exactly.
I had a very basic one actually.
It's okay. They're usually the hardest ones to answer.
In
the beginning you showed kind of a theoretical picture about the particle emission, that you compare the independent particle picture with the quantum particle picture. Now my question is, at your final, just this slide, sorry, your experimental data. Yes, this one. Do I see correctly then that you can basically say that near the Fermi level you have this independent particle picture, but at the 300 MeV line,
No.
way lower.
No, so the independent particle picture is nowhere. There is no known material that has delta functions as its spectral function. Right, so maybe you could argue for a very pure sample of gold or copper or something like that, or maybe even better, you should take sodium or something which is just an S electron metal. The one right at the Fermi level for a perfect crystal, which of course doesn't exist, could be a delta function if you had a perfect spectrometer, which you don't. But in all of these cases, the growth of the width as a function of frequency is often not omega squared and t squared. So here you have something which is growing as a function of omega as we go down, right, in a way which looks like a power law. And right at the Fermi level, if you cut this thing horizontally, it looks like a Lorentzian because this K-dependent self-energy hasn't kicked in yet because we're at Kf. And the deeper we go, the more asymmetric it gets. You can see there's something even more pathological in such data here, that you have a part. No one's asked me about it yet. It looks like the dispersion is vertical. That's weird, right? So we don't know what that is. So we just stay clear that we stopped our analysis around here. This is about the 350 millivolt line.
The broadening itself that you can't see, so there is broadening of the peak.
Yes.
Is this a quasi-particle effect?
So the broadening of the peak is telling us it has a finite lifetime. Right. So here at the Fermi energy, I should have added one higher energy. It's as narrow as it can get, and if we go down here, let's say we go to 0.1 eV, this is going as linear in frequency. So this will then be some peak. Let me try and draw it. It's going to be coming out here like that. I can do it with chalk.
For different colors.
So the very narrowest one will be like this, and then we'll start to get something broader and broader. Of course, its integral is the same. There's a spectral weight sum rule.
Is this all due to the lifetime, or?
This is all due to lifetime, but the lifetime can be due to many things, right? The lifetime, the one I've been discussing, the one that Henk is computing, is the electron-electron interaction. But of course, if this electron bounces into a lattice, a phonon, then it will also change its lifetime. Everything is in there. The whole of physics is in there as a lifetime, but we can just measure the sum. But at least this phonon coupling gives structure because the phonon has a given energy. So when we see a step at that energy, we say, okay, we put a step. But the one which is of interest in the holography world and in the cuprates as a whole, because of this fact that the superconductivity is a next door neighbor to strongly correlated magnetism, is the width of this part that's coming from the electron-electron interactions. But it doesn't come with a label in the experiment. It comes with a magnet. So it's half of this width.
Can we call this one quasi-particle, like a broadening itself?
Very quickly, the half width of this object translated into energy terms is larger than its energy. So in the Landau definition, no. The other extreme theoretically is the holographic one, which says there are no particles, let alone quasi-particles. That's valid for this particular doping level up here, where the TC is maximal. So it's a difficult, it's a sticky wicket, to use an English expression for cricket. And so when do you call this thing quasi-particle, when you don't? That's a really hard quantitative judgment, which you need very, very good experimental data.
Thank you.
Thank you, Mark, for a nice presentation. Let's thank Mark again. We'll have the next installment, I think, in 2 weeks.
Who's next?
Who's next?
The next is Alberto Abo.
No, it's coming in the 30th, so
We love
It's the
going
30th.
talking.
yeah,
Ah, okay.
30th.
Very nice talk.
Yes.
Is it?